Hello everyone, and thanks for joining Innovative Sensor Technology for our webinar on flow measurement using thin film sensor technology. Here's a quick overview of what we'll cover in the presentation. We'll start with some flow terminology. Then we'll learn about the types of thin film mass flow sensors. When we discuss how they work, we'll go in depth, exploring the anemometric and calorimetric flow principles. Then we'll take a look at a typical flow sensing circuit. We'll wrap up the flow presentation with a trip to IST AG's cleanroom, where we'll walk through the fabrication of an FS7, one of our most popular flow sensors. All right, let's get started with flow. What do we use flow sensors for? A flow sensor is generally used to measure gas or liquid flow rate. Let's say we have a car driving from point A to point B. The flow speed in this case would be the distance the car drives in a certain amount of time. For example, 30 miles per hour. We'll use different units when measuring gas and liquid flow, but it's generally the same idea. Flow sensors can be utilized in many application areas, including industrial equipment, compressed air systems, HVAC, automotive, like air intake or exhaust for example, medical, like patient oxygen systems and ventilators, and device monitoring. How do we usually express flow? The flow speed is the linear velocity of the flow. This is expressed as a distance over time, for example, meters per second. Then we have the volumetric flow rate. This is the volume of our gas or liquid which moves through a given cross-sectional area per unit time. This is expressed as volume over time. For example, we might have cubic meters per second. A few others we commonly see are standard liters per minute, or SLPM, milliliters per minute, and cubic feet per minute. So, how can we calculate the volumetric flow rate? First, we take our flow speed, which we know is our distance over time. For the volumetric flow rate, we multiply the flow speed by the cross-sectional area of our pipe or our duct. In the example on the left, the area is simply pi times the radius squared. There are many different measurement technologies available for flow. Some are more suitable than others for certain applications. Some common ones include electromagnetic, Coriolis, ultrasonic, differential pressure, vortex, and thermal mass. At IST, we specialize in the standard and custom thermal mass flow sensors. Let's get into how these sensors work. There are two thermal mass flow principles we use with our sensors. The first is the anemometric principle. An anemometric flow sensor consists of a temperature sensor and a heater on a single chip. In our case, we use platinum meander structures with different resistances, just like with our thin film RTDs. To learn more about RTDs, check out our temperature webinar. When we work in constant temperature anemometer or CTA mode, we set a certain temperature difference between the sensor and the heater, which is constantly maintained at any given flow speed. It should be noted that material selection is super important when it comes to thin film flow sensors. For RTDs, we typically use an aluminum oxide substrate with high thermal conductivity. That way, the whole chip takes on the temperature of its environment. With our flow sensors, however, we use a different substrate material with low thermal conductivity. We do this because we want the temperature sensor to be thermally isolated from the heat generated by the heater. Let's take a closer look at measuring in CTA mode. Here we have an FS7 flow sensor fitted in a pipe. Using sensor self-heating, the heating element heats the surrounding medium. Depending on the flow rate, more or less heat will be carried away from the flow sensor. The temperature sensor measures the medium temperature around the chip. For flow measurement in CTA mode, we specify a certain temperature difference between the sensor and the heater. Let's say, for example, 30 degrees C. When there's a flow present, the heater's self-heat is carried away. Additional power is immediately applied to the heater to rebalance the sensor bridge and maintain the specified 30 degrees C temperature difference. The additional power caused by an output voltage increase is what we're going to measure. Then we'll convert this to a flow speed. If we happen to know the pipe's diameter, we can also convert this into a volumetric flow rate. So what does this look like? Let's take an example of a flow signal using an FS7 mounted in a 5 mm diameter tube. The medium is nitrogen at 25 degrees C, and our temperature difference is set to be 30 degrees C. We perform the measurement using a CTA circuit, which I'll show a bit later. The output signal is adjusted to 3 volts at 0 flow. This corresponds to our temperature difference of 30 degrees C. As you can see by the slope, the sensor has its highest sensitivity at lower flow speeds. Let's see a quick overview of the CTA measurement circuit. It consists of a simple feedback circuit for the temperature regulation of the heater. The red rectangles represent different resistors in the circuit. The circuit compensates for temperature variation in the medium using the temperature sensor on the flow chip. The temperature difference, 30 degrees C in our previous example, is set by resistor R3. Resistor R2 should be adjusted within 10% for calibration. Resistor R7 is included for anemometer stability. For more details about this circuit, please check out our application note on our website. So, how do we characterize our CTA results? The CTA is described by King's law, which we have here. We convert and simplify it to get this formula where U represents the CTA output in volts. Next, we use the reverse function and linearize. What about the K and N values? We can determine these by performing a calibration using 3 points, which are 0 flow, the midpoint of our flow measurement range, and the upper limit of this range. For a more detailed description of this process and to see an example calculation, take a look at our application note. Now that we know about the anemometric principle and CTA mode, let's talk about the calorimetric flow principle. With this, we can measure both flow speed and direction. The CTA mode just gave us the flow speed with no direction. Let's take a look at our FS2 sensor. It consists of a heater element with temperature sensors positioned on either side of it. You'll notice that on some of our calorimetric sensors, like the FS2 and MFSO2, we have an additional temperature sensor. This is used to measure the ambient temperature or can be used to operate the FS2 in CTA mode or in combined CTA and calorimetric mode, which we'll touch on later. Let's visualize the calorimetric principle. The heater is supplied with constant voltage or current in the case of the FS2 or MFSO2, or constant power in the case of the SFSO1. It creates self-heat, forming a heat cloud around the heating element. With no flow, the heat cloud is symmetrical. Both of our temperature sensors will read the same. When flow starts from either direction, some heat is carried away from the heater in the direction of one of the sensors. The temperature difference between the two temperature sensors can be converted to a flow rate, up to a maximum specified flow speed. The temperature difference also tells us the flow direction. I mentioned the CTA and calorimetric combined mode before. Let's take a look at this using an MFSO2 chip as an example. Calorimetric flow sensors can measure flow speed and direction, but at high flow speeds this doesn't work well. The relationship between flow speed and temperature difference breaks down. When we want to measure these higher flow rates, we can combine the CTA and calorimetric modes using the additional temperature sensor, outlined in red here. We start running the sensor in CTA mode, changing the power to the heater and maintaining a constant temperature difference between the heater and the sensor. The other two sensors near the heater are then used to determine the flow direction using their temperature difference. By combining CTA and calorimetric mode, we extend the flow measurement range of our sensor. The modes monitor each other, so the calorimetrically measured zero flow point can be used to adjust the zero flow signal of the CTA. Now let's take a look at the standard thermal mass flow sensors from IST. From left to right, we have the FS7, which is a gas flow sensor that works in CTA mode. The FS2, a gas flow sensor which can operate in either or both CTA or calorimetric modes. The MFSO2, a gas sensor which can also operate in either or both modes. The silicon flow sensor, or SFSO1, which is a gas sensor for calorimetric mode measurement. And lastly, the out of liquid, or OOL, a liquid flow sensor which uses CTA mode. While we don't recommend using the gas flow sensors in liquid, some of them can work in certain oil flows. Get in touch with us to discuss your application. For the gas sensors, let's take a closer look at each model. The FS7 is suitable for many flow applications up to 100 meters per second. It comes as a bare chip or in a plastic housing for easy integration. The 4W version is usable up to 400 degrees C. Next up, we have the FS2, a versatile option for applications where you want to measure direction along with the flow speed. Then we have the MFSO2, which is optimal for fast measuring of flow and direction. The heater and sensor are on a membrane structure, which gives us ultra-fast response time. It's available as a bare chip or mounted on a PCB for easy connection. Finally, we have the SFSO1, which is based on silicon. Like the MFSO2, the active elements are on a membrane, giving us a very fast response time. One of its key features is its low power requirement. What about liquid flow? For this, we have the out of liquid or OOL flow sensor. It consists of two tiny RTD elements attached directly to the stainless steel tube. It works just like the FS7 using CTA mode. The RTD with the white wires measures the ambient temperature flowing through the pipe. The one with the red wires acts as the heater. There's no direct contact with the liquid since the sensors are located on the outside, so it's good even for corrosive liquids. We have excellent thermal coupling between the active elements and the medium since the chips have metallized backsides. A few different tube diameters are available. If you're working with tubes larger than 15 millimeter, we have another solution called the Real Probe Flow or RPF. This works exactly the same way, except the RTDs are located in probe tips. The probes are mounted inside the pipe or duct. The probes are very similar to IST's Real Probe Temperature Probe, which have very good response time. We're often asked, how should the sensor be mounted in the flow path? If you're using a duct flow probe, be sure that the sensor surface is parallel with the flow, meaning the flowing gas passes smoothly over the active sensor surface. The same goes for a duct or a pipe. One of the useful benefits of the FS7 with housing is that it has a small tooth sticking out on the side. Many of our customers choose to add a notch in the hole that they drill on their pipe. This makes it easy to position the sensor perfectly parallel with the flow. So, how do we make these sensors? We do this in a carefully controlled cleanroom environment. Here, I'll just give a quick overview for an FS7. If you want a more detailed view of each step, I recommend checking out our temperature webinar, which goes a little more in depth. First, we start with our bare substrate, which remember has a low thermal conductivity. Then, we deposit our platinum resistive layer using plasma-enhanced physical vapor deposition, also referred to as PEPVD or sputtering. We then create our meander structure by spin coating a photoresist layer over the entire substrate, then using lithography, followed by etching, to create the meander and pad structure. Next, we have two screen printing steps. During one, we apply a glass passivation over the chip. During the other, we apply a platinum paste on the contacts to allow for a better weld later on. Each screen printing step is followed by a high temperature process to harden the paste. We dice the substrate into strips, then weld our wire using a semi-automated welding machine. After applying a glass paste and hardening it, the sensors are separated using another dicing step. At the end, we test each sensor for temperature measurement accuracy using a finely controlled bath. For sensors with short wires, we can test many sensors at once. As I mentioned, this is just a quick overview. Along the way, there are a lot of other steps, including laser trimming, chemical cleaning, high temperature processes, and inspections. Along with standard sensor components, we can also customize sensors for your particular application. Here are a few examples of potential customizations. We can provide the sensors in custom housings, mount them on special PCBs, or provide them with customer-specified cables and connectors. Like with our other sensor types, we can also customize the wire material and length. Here are some examples of ones we use for our temperature sensors. Many of them can be adapted to the flow sensors as well. As a technology partner and resource, IST's application engineers can also work with you on your electronics, custom tailored to your flow measurement application. Last but not least, we have evaluation kits available for most of our sensor models. Our customers often use these to evaluate the sensors for their applications. Some of the kits can also be integrated into customers' assemblies. Take a look at the data sheets on our website for more info. And that does it for flow measurement using thin film sensor technology. Along with these sensors, IST also offers a variety of temperature, humidity, conductivity, and biosensing components. We invite you to visit our website, www.ist-ag.com, and reach out to us to discuss your application. Our technical staff can discuss our many standard products and give you insight into our simple customization process. If you have any questions, get in touch with us anytime at info@ist-ag.com. Thank you everyone for watching. And again, feel free to contact us anytime to discuss your sensing needs. Check our website for your local contact info. You can also reach an IST team member using our website's live chat, available 24 hours a day, Monday through Friday.